Hello, in this lecture, we're going to be discussing antiderivatives and indefinite integration. Let's start with a simple example. Let's say we have f of x equals 2x. So a question we might ask is, what is a function whose derivative is 2x? So what is a function whose derivative is 2x? Whose derivative is 2x. And it's a pretty easy question if you already know calculus. You might say x squared, right? X squared is an example of a function whose derivative is 2x, because you can bring the 2 down and you can subtract 1 from the exponent, and basically just applying the power rule and you'll get 2x. I'm going to give this a name. I'm going to call it big F of x. And this is an example of what's called an antiderivative. So this is an antiderivative. So we would say that x squared is an antiderivative for 2x because the derivative of x squared is equal to 2x. So the thing is, there's other possible answers. For example, let's say I say big F of x is equal to x squared plus 1. Well, if you take the derivative here, you're going to get the same thing. You're going to get 2x. The derivative of x squared is 2x, and the derivative of 1 is 0, so you're going to get the same answer. So this is also an antiderivative for 2x. In fact, we can look at big F of x and call it x squared plus any number. I'll use a capital C. And this is also an antiderivative for 2x. This one has a name. This one's called the general antiderivative. And this C here, it's an arbitrary constant. That's the word we often use. Arbitrary constant. So it could be any number. We don't know. That's an R there. Arbitrary. This is hard to read. So arbitrary, arbitrary constant. So there's infinitely many antiderivatives for 2x. Let me just go ahead and give you the definition so you have it in one place. So we say a function big F is an antiderivative. So antiderivative of little f on some interval I. So I'll say on an interval I, if whenever you take the derivative of big F, it's equal to little f, and this is true for all x in your intervals. So for all x in I. So that's the definition of an antiderivative. And typically in a calculus class, you do use this, but in the actual problems that you do in calculus, you don't use it too much. This would come up a little bit more in maybe a proof-based class or something like that. The point is though that there's infinitely many, right? There's infinitely many. And now let's talk about what integration is. And I'm going to give you the notation. I'm going to switch colors here. Oh, before I do though, let's actually do it with respect to this example. So that way it doesn't look so abstract. So here's the notation that we're going to use. So the process of finding an antiderivative is called antidifferentiation, right? We're going backwards. So instead of differentiating, we're antidifferentiating. And here's the notation we use. So we have this elongated S symbol. This is called the integral symbol. So it's the integral symbol. And here we have 2x, and then we have dx. And we said that our best answer was this one, x squared plus c. So in this example, which we did in our head, we looked at the 2x and we said, what's a function whose derivative is 2x? We said x squared. This is the notation you would use. So this process of finding an antiderivative is called antidifferentiation or integration. So this piece here has a name. This is called the integrand. It's really important to know this because when you're talking to people about mathematics, you say, well, my integrand, I couldn't factor it, or, you can talk about the integrand because you know what it is. This piece here, this dx, this tells you what variable you're integrating with respect to. So I'll just say variable of integration. So because it's math, we have more than one variable. Sometimes we integrate with respect to y, in which case you would put a dy. Sometimes you do theta, sometimes you do r. If you study multivariable calculus, you'll do x, y, and z in the same problem. So you'll have dx, dy, dz. So it tells you the variable. So here the variable is x. This here is our antiderivative, x squared. In fact, this whole thing is an antiderivative. You could say x squared plus c is the antiderivative, but I'm just going to single out x squared just so I can label this one as well. This one has a name. We called it an arbitrary constant, but it's actually called the constant of integration. Okay, it's the constant of integration. It's really important to include it. There's infinitely many solutions, right? There's infinitely many choices for C. There's infinitely many antiderivatives. Really, really important to note. And this elongated S looks like someone took the letter S and stretched it. This is the integral symbol. So again, this process of finding a function whose derivative is 2x, this process of going backwards, it's called antidifferentiation or integration. This is called an indefinite integral. So indefinite integral. I'm going to write that down. So this is an indefinite integral. A natural question then comes into play. What is a definite integral? A definite integral is different. You're going to have like numbers here, like you might have a 3 here and a 4 here. That's called a definite integral. Those are studied later. You have to learn about Riemann sums and some stuff like that. But for now, we're going to stick with indefinite. So in general, to do this, it's pretty tough, right? Like we had to, I picked this example for this video because it's easy, right? So I wanted to pick something that most people who know very, very basic calculus can do and understand. Yeah, okay, what's a function whose derivative is 2x, x squared? But if I say, hey, what's a function whose derivative is, x plus 1 over x cubed plus 1 minus the secant of x? Like, what's that going to be? Well, it's a little bit more difficult, right? So you need formulas in order to do these problems. So now I'm going to give you a list of all of the basic formulas that you need for integration. So formulas. And we'll justify each one, at least logically. And in some cases, I'll be able to give you an example. In some cases, I really won't, not until later. So the first formula we're going to look at is if we're trying to integrate 0. Okay, 0. We're looking for the antiderivative of 0. We're trying to antidifferentiate 0. So lots of ways to say similar things. So this integral, we have to integrate 0. So you ask, what's a function whose derivative is 0? Well, any constant function will work. Let's just go with c, right? C will work because if you take the derivative of c, you're going to get 0, right? The derivative of a constant is 0. So that one's pretty easy. How about this one? Let's say we have a constant, which I'll call k, with respect to x. So the variable is x. What's a function whose derivative is x? Well, it's going to be kx. And then, of course, plus our constant of integration. And you can always check your answer. If you differentiate this, you should get the integrand. See how important it was to know what it's called? It helps to know. So the derivative of x is 1, so we just get k. And the derivative of c is 0, so it goes away. Let's do an example with this one. We can do a simple one. Let's say we want to integrate 2 with respect to x. So in this case, there's 2 ways to do it. Method 1, you ask yourself, what's a function whose derivative is 2? 2x. And then don't forget the plus c. Method 2, which is the way I do it, which is much more mindless, it requires less brain cells. You see the 2, it's a constant by itself. You just put an x next to it. Simple, right? Doesn't matter how tired you are or how much math you've been doing. If it's a number by itself and it's with respect to x, you put an x. Actually, this leads me to a point. Let's say instead it was 3 d theta. Hey, what? What's going on? Trig? Yeah, I want to introduce a theta. Why not, right? So in this case, it's 3 theta plus c. So it depends on the variable. That's the purpose of this. It tells you what the variable of integration is. So in this case, it's d theta, so we put a theta. If it's dr, you put an r, etc. All right, let's go to our next formula, which I'm just doing these off the top of my head. How about this one? If you have a constant times a function, okay, you can pull the constant out because it doesn't depend on the variable x. So this is equal to k times f of x dx. This will come up sometimes later. Just know that if you have a number, you can pull it out and there's no issue. As a concrete example, I guess I could do one here. It's a little bit silly, but let's do it. Let's say you're trying to integrate 5 with respect to x. You're saying, I don't really like the 5, so I'm going to pull it out. So you pull it out, and you're just left with 1 dx. And you say, oh, 1, I can integrate 1. That's just x, right? Because 1 times x is x. The derivative of x is 1. So the integral of 1 is x, rather. So to integrate 1, you just use this rule, right? So you just put an x next to it. So you just get 5x plus c. So a pretty useless move here, right? So you integrate this, and you get x, and then you just multiply by 5 and you get your answer. So not very useful in this particular case, kind of a pointless example. But the point is you can pull numbers out, which can be useful sometimes, just not in this particular case here. This next rule is very useful. It says if you have more than one term in your integrand, you can separate it into two integrals. So if you have, say, f of x plus or minus g of x with respect to x, you can break this up into two separate integrals. We have the integral of f of x with respect to x plus or minus the integral of g of x with respect to x. Very useful. And once we know more, I can do an example of this. But basically, it means you can integrate term by term. If you have 5 things, you can break it up into 5 integrals. That's okay as well. 5. This next one's really important. It's called the power rule. There's so many power rules in mathematics that it almost pains me to use the word, but it's okay. Context is key. So this is the power rule for integration. So if you have x to a power, say x to the n, and you're integrating this with respect to x, so what you can do is basically you just take the exponent and you add 1. So this is x to the n plus 1, and then you just divide by the 1, and then you add your constant of integration, capital C. So very, very powerful rule. Now, if you're thinking like, I don't want to say a math person, but sometimes you get into the habit of thinking, when doesn't it work? Well, when doesn't this work? Well, if n is -1, it doesn't work. So this is only valid for n not equal to -1, okay? And the natural question then to ask is, what do you do when n is -1? I'll show you, and I'm going to put it in red up here. If you have x to the -1, this is later. This is going to be the natural log of the absolute value of x plus c. And this is something you learn later in calculus. We're not going to be discussing it in this video. It's taught much later. But for every other choice of n, you can use this formula. So very powerful. Let's do an example right away so you see it. So let's say we have to integrate x to the 4th with respect to x. So in this case, a newcomer to the study of calculus might say, okay, so the exponent here is 4. This is the value of n. So if I'm going to apply this formula, it's x to the 4 plus 1 over 4 plus 1 plus c. And that would be 100% correct. And so this is equal to x to the 5 over 5 plus c. So this would be the answer. Now, in general, you do want to eventually move past this type of computation. You want to eventually skip this work because it really clutters your problem. So when you see a problem like this, let's just say x cubed dx, you basically jump to the solution. 3 plus 1 is 4, and then you just divide by the 4, like that, plus c. So you want to skip this middle step. It's not wrong, it's just, it really like slows you down, and it's just, the math gets really long and involved. So anytime you can skip a step that's very, very easy to do mentally like this, it's recommended that you do. And this just doesn't look pretty when you have 6 of these in the same problem, you know, so worth just going to the answer. So very, very powerful formula. Okay, I think what's left now are the trig functions. I guess I've been numbering these, so I'll call this one 6. And the trig functions often intimidate people because people see these formulas and they think, oh, wow, I'm supposed to memorize all of these. You are, but at the same time, you can think about them a little bit differently. So I'm going to show you how I think about these, and maybe that will work for you. So let me just switch colors here. For some reason, my pen got really thick. I can control how thick my writing is. Watch this. I can write really thick, or I can write really thin. I'm just trying to find a happy ground here. Here we go. Let's try this one. So let's try to integrate. That's pretty good. Oh, I'm using graffiti pen. There we go. Let's go back to pen. Let's try cosine x. There we go. Back to regular writing. The integral of cosine x. So when you're trying to integrate cosine, you're asking yourself, what is a function whose derivative is cosine? Sine. This is sine x, but that's not it. We still need the plus c. So pretty easy. So whenever you look at the integral of cosine, if you don't have it memorized, you can memorize it. You can say, hey, the integral of cosine is sine. But maybe you're just having a hard time finding room in your brain to memorize it, and you're just refusing to memorize things, which I have a habit of doing. I like to know how things are derived, and it's just a habit. So you're trying to integrate cosine. You say, oh, I forgot what that was. Oh, but wait, what's a function whose derivative is cosine? Oh, sine. The derivative of sine is cosine. Yep, checks. You differentiate this, you should get your integrand, and it certainly works because the derivative of sine is cosine. What about this one? There's a reason I did cosine first, because it's easier. This one's harder. So what's a function whose derivative is going to be sine? Well, the derivative of cosine is negative sine. So this is going to be negative cosine x, and then plus our constant. And you can check, right? The derivative of cosine is negative sine. We've already got a negative here, so negative and negative is positive, so life is good. How about this one here? Secant x, tangent x. These are strategically picked, by the way. You might say, what about secant? Why'd you jump to secant, tangent? Secant is a whole nother story, right? Integration is not as easy as differentiation. The integral of secant requires other techniques, which we'll learn later. So you have secant times tangent. What's a function whose derivative is secant tangent? Well, secant. This is the secant of x plus our constant of integration, capital C. And how about secant squared? That's another one we can do now. Secant squared x dx. So what's a function whose derivative is secant squared? Well, that's just going to be tangent x plus c, right? Because the derivative of tangent is secant squared. And then we get to the unpopular ones, the ones that don't come up so much. Cosecant x, cotangent x, dx. So what's a function whose derivative is cosecant cotangent? Well, the derivative of cosecant is negative cosecant cotangent. So this requires a negative cosecant x plus c. Again, the derivative of cosecant is negative cosecant cotangent. We've already got a negative, so it will become positive. And the last one we're going to discuss in this video, the last formula, I know it's a lot of formulas, is cosecant squared x dx. And in this case, you ask yourself, what's a function whose derivative is cosecant squared? Well, the derivative of cotangent is negative cosecant squared, so this is going to be negative cotangent of x plus our constant of integration, capital C. So, wow, that's a lot of formulas. And usually when people first see this, they're like, OMG, how am I ever going to know this? But how did I just go over it, right? It's just all derivatives. So it's really the derivatives that give you the integrals. And at least for me, that seems to work better. It stays in my long-term memory. It just works better because, you know, you integrate other stuff besides these things. You know, you might have to integrate sine to the 4th power someday. That requires trig identities, requires a lot of knowledge. So I just feel like the less you memorize sometimes, the better. And thinking about it in terms of differentiation makes it a little bit easier. Let's go ahead and do an example. I'm going to switch back to white. And let's just do a simple example here. Let's say we have x to the negative 4, maybe not so simple, plus 5 plus sine x dx. So now we have 3 terms, right? 3 terms. And we saw earlier that one of the rules said if we have 2 terms, we can break it up into 2 pieces. But if you have 3, you can do it also. You can break it up into 3. The rule can be easily generalized to any finite number of terms inside the integrand. All right, so let's just jump into it. By the way, when you integrate, you drop the integral sign and you drop the dx, okay? So we're going straight to the answer here. So here, we have x to the negative 4. So we can apply the power rule. So we'll add 1 to that. So it'll be x, negative 4 plus 1 is negative 3. And then you divide by the negative 3. Okay? Plus, you have a number by itself, just tack on an x. Trig function. What's a function whose derivative is sine? Well, the derivative of cosine is negative sine, so this is going to be negative cosine x, and then plus our constant of integration, capital C. It's not good form to leave your answer like this, so the negative on the bottom looks bad. I'm going to write it like this. Negative 1/3 times x to the negative 3 plus 5x minus cosine x plus c. And that would be an acceptable final answer. Some people ask about whether or not you should bring this down, like this piece here, and write it like this, negative 1/3 1 over x cubed. I think it doesn't matter. Different people do it different ways. I've seen solutions in the back of books. They do it this way, they do it this way. Some people will do this, which I really don't like. It's just more work. I personally prefer to leave it like this. So that is a simple example of indefinite integration.